Thank you.
So today we are going to present our work on a more programmable and performance optimized virtual switch. This paper was written by the two of us, myself and my teammate Namrata Limaye, and today we are going to make a short presentation on that. Sebastian, next slide, please. So right from the time that we started running multiple applications on multiple virtual machines, the need for a software switch to coordinate networking resources across them became really important. And Open vSwitch, an initiative started back in 2009, an open source initiative, is really today the ubiquitous solution for this. It's used almost everywhere. There are some cloud service providers who have even come up with their own customized version of this. And but with the popularity of OVS, there are also some challenges. I mean, in particular, from 2009 to today, the network has moved from hundreds of megabits to hundreds of gigabits, and to scale up to that, we really need to offload OVS in hardware, and there we we face some challenges, and we'll talk about those challenges and what is the solution that we provided. Sebastian, next slide, please. So this is OVS. It's a virtual switch implemented in software. It has a flexible controller in user space, and if the first packet of every new flow goes to this user space to get their match action pipeline configured, and then from that point onwards, all the subsequent flow can entirely run in hardware, and that fast data path can either be in the kernel or it can be implemented in hardware. Um, so this is the structure of OVS, as you can see here. Next slide. So as part of our overall work to do hardware offload of infrastructure as a service, here are some of the things that we observed for OVS. Um, OVS maintains flow cache, and there is a micro flow cache and there is a mega flow cache also. The mega flow cache is actually a great software optimization idea and reduces the number of flows to manage, but it can be slow, and the potential tuple space explosion problem associated with it can lead to denial of service attacks. Also, this behavior that we call the reactive behavior, which means that the flows are not configured a priori, it has to be sent to user space once to get it configured. It also increases the slow path performance expectation, and it also makes maintaining a very high flow setup rate. Today, the CSPs are asking for multiples of millions of flows set up every second. So that becomes a challenge. And then, most importantly, this aggregation disaggregation problem that we highlighted in our paper. So essentially, when you have applications coming in, whether it's a access control list application or whether it's a virtual routing application, just the application themselves tell you what the intent is and what kind of hardware they can make use of. For instance, the vRouting can use a longest prefix match support in hardware. The ACL might use a exact match support in hardware, etc. But after passing through the OVS caches, then one flow pretty much becomes undistinguishable from another flow. And so the original intent is lost, and then it becomes a challenge to rediscover the intent and map uh, efficiently to hardware. And so the solution that we came up with is to skip these caches and to be able to go directly from the application level tables to the hardware tables that the hardware supports. So that is our key innovation, so to say. Next slide. So this is our P4 enhanced open vSwitch. What the way we started this work is we made a fork of OVS and did our development. And today, the GitHub that any of you in this audience can actually access. We are running an initiative for infrastructure programming called IPDK. There is a website called ipdk.io where this code is available from GitHub, and we are actively working on upstreaming it in the OVS repo itself. So the OVS interface that everyone is familiar with is called OF Proto, and what we have done is we have created a parallel interface called the P4 Proto. And so with our reconfigured OVS, we are actually offering three control planes, and the customers are free to choose whichever they want to use. They can do the OVS configuration mapping directly to P4 table. If you are coming through P4 runtime APIs, then you can also use OpenConfig for your configuration, and this is used in the container load balancing work just discussed by Nupur and others. And there can be a kernel path also that we are working on. And multiple clients can connect and utilize this pipeline. Next slide, please. So So these are the key software components, the different pieces. There is a rectangle shown as table APIs. This is essentially the lowest layer that actually connects to the hardware, and this layer can be very quickly and efficiently ported to different hardware targets such as ASICs, FPGAs, etc. And that's how we want this to behave. Next slide. These are some of the locations for the code. You can go to github.com, look for IPDK IO.